Okay, hello everybody, Mr. Lau here. Okay, so today what I'm going to do here is I'm going to do the lecture for lecture 2, which is this first law of thermodynamics. All right. So this chapter 2 is all about the first law. Okay, so what we're going to go through here is we are going to go through the introduction. I'm going to give an introduction of what the first law is. Okay, followed by the two main equations that is packed to this first law. Okay, namely the non-flow energy equation and also the steady flow energy equation. All right. So first of all, let's take a look at what is the first law. Actually, this first law has long been known by you or most of the students out there. Okay, something that we actually learn in primary school, in fact. Okay, basically, it's just the principle of conservation of energy. All right. So we all know that energy can neither be created, okay, nor destroyed. Okay, but instead it can be transformed or transferred from one form to the other. Okay, so that is basically the first law. Okay, and this law will govern all energies in the world. Okay, it cannot be created, cannot be destroyed, but it can only be transferred or transformed from one form to the other. All right, for this module, okay, we are specifically going to refer to this energy transfer in the form of heat transfer and also work energy transfer. All right, because if you remember from the previous chapter, okay, what we are looking at is actually to be able to transform heat energy to other forms of useful energy, such as electrical, such as kinetic, such as mechanical energy, which can help us to do work. Okay, so that's why it's so important to understand the first law. Okay, so next, uh, so this first law, all right, can be understood from a few different perspectives. Okay, what we are going to do here is we are going to write a mathematical equation to represent this first law. Okay, because we wish to do some calculations at the end of the day. All right. So if you are talking about the first law applied to a thermodynamic cycle. All right. So what is a thermodynamic cycle? Okay, a thermodynamic cycle basically is a process whereby it is cyclic. All right. So for example, okay, the example is the refrigerant in your aircon. Okay. So for example, the refrigerant in aircon, it starts from the air compressor. Okay, we call this state 1. Okay, I'm not going to go through all 4 processes within the aircon, but this aircon refrigerant is going to undergo a cyclic process. Okay, and it's going to go back to its original state. Correct. So from the compressor, it will go on to the evaporator to the expansion, and then you'll go back to the original state. So in this case, this is an example of a thermodynamic cycle. Okay, so it will go one round and go back to its original state. All right. So the refrigerant is recycled every single time. Okay, so for such a cycle, okay, we say that the net heat that is applied to the system must be equals to the net work done on the system or by the system. Okay, why? Okay, so because you see, what kind of interaction can this cycle happen? Okay, there can be heat. Okay, heat exchange. Heat can go in or heat can come out. All right, same thing. Work can go in and work can come out. All right, but more importantly, the state of the refrigerant doesn't change. So the start and end point remains the same. All right, that means from the start to the end, okay, the fluid that we are working with remains at its original state. Okay, so for this case, there's no change in any other things. Therefore, we can safely say that the Q must be equal to W based on the conservation of energy. All right, so this here we have is our first equation, okay, whereby we apply this law of conservation of energy to a cyclic process. Okay, the sum of all heat must be equals to the sum of all work. Okay, of course, some of you might not be very confident with this highly mathematical symbol, which is the sum. Okay, so instead, maybe you can just simply write Q in plus Q out is equals to W in plus W out. All right. Okay, and take note, if we were to apply this equation, all right, we need to follow the so-called the convention, the sign convention, which we studied in the first chapter. All right, so in this case, Q in is supposed to be positive. Q out will be negative. W in will be negative, and W out will be positive. Okay, so before we plug into this equation, make sure we follow this sign convention, right? Okay, good. Let's move on. Okay, yeah. So this slide here is exactly what I've said just now. Okay, can. So if it is a work output, it's going to be positive. Work input is going to be negative. Heat loss is negative, and heat supply is positive. All right. Okay, so let's go through this example, this simple example over here. Okay, so if let's say this system undergoes a complete thermodynamic cycle, again, the keyword here is it must be a complete thermodynamic cycle. That means the fluid is recycled. Okay, so determine the value of the work output of this system. Okay, so the system is given here. Okay, Q out today is given, Q in is given, W in is also given. All right, so we apply the first law, okay, for a complete thermodynamic cycle, which is Q in plus Q out equals to W in plus W out. Okay, so since we want to find out the W out, we will rearrange the equation to make W out the subject. Okay, then we plug in the values. So when we plug in the values, again, must be very careful. Q in, all right, over here, the value is given to be 10 kilojoules. Q in is supposed to be positive, so we'll put in 10 times 10 to the power 3. Okay, Q out is given to be 3 over here. All right, numerically 3. But when we put into the equation, because it's out, all right, so we must put in a negative 3 times 10 to the power 3. Okay, same thing, W in numerically is given to be 2. But since, based on the convention, W in must be negative, so we must put in negative 2 times 10 to the power 3. All right, so work it out and you will get your final answer of 9 times 10 to the power 3 joules or 9 kilojoules. All right. Okay, let's move on. Okay, so we are now done with discussing a complete thermodynamic cycle. The other process that we're going to talk about is actually non-flow process. Okay, so in a closed system, energy may be transferred across the boundary in the form of work energy and heat energy. Okay, but the work fluid itself never crosses the boundary. Okay, so as the name implies, it's supposed to be a non-flow process, meaning to say that we do not expect any flow of the fluid. All right, an example will be the fluid within a piston. Okay, no matter how we move this piston, okay, the fluid that is entrapped within the piston remains inside. Okay, unless there's a leak. All right, so this is an example of a non-flow process. Another word for the non-flow process, okay, can be represented by this called the closed system. Okay, so since the fluid is not able to cross, so what can you cross from the boundary? Okay, of course, it can be heat and it can be work. So only the work energy and the heat energy can be transferred across the boundary. Okay, so any process that undergone by a closed system is actually referred to a non-flow process. So these two terms come hand in hand. When we talk about non-flow process, usually we are looking at a closed system. Or when we are looking at a closed system, we are looking at a non-flow process. Okay, basically the idea is that the fluid cannot cross the boundary. Okay, so here we're going to show an example or interesting example of a non-flow process. Okay, so this process that we're going to look at is going to happen in a 4-stroke combustion engine, which is the engine within your motor vehicle, your cars. Okay, so usually the car engine is 4-stroke. What do you mean by 4 strokes? Okay, because it undergoes 4 different types of stroke that we see down here. Firstly, suction stroke. During the suction stroke, okay, the valve of the piston engine will actually open, okay, to let the working fluid come in. So in this case, if you're talking about a car, the working fluid is actually none other than air. All right. Okay, so once the air comes into the piston, okay, there's actually a secondary step whereby the fuel injector will inject the fuel into the piston engine. So within here, we are going to get an air-fuel mixture. All right. So once this is done, the valve will close. Then you move on to the second step, which is the compression stroke. So the piston will push up and cause the mixture inside to be compressed to a high pressure. All right. So this now inside is a high pressure air-fuel mixture. All right. So if it is a petrol car, all right, then there will be something called the igniter or the spark plug. So the spark plug will operate by giving a spark. So when this happens, okay, you move on to the third stroke, which is the working stroke. So when the spark plug sparks, there'll be an explosion, a mini explosion within the piston, so which causes the air and fuel mixture to rapidly expand and push the piston out. All right. So the difference here is if it is a petrol engine, there will be a spark plug. All right. But if it is not a petrol engine, it's just a diesel engine, there won't be a spark plug. Okay, if it is a diesel engine, the compression will take place until it reaches a certain enough pressure that auto ignition takes place. Okay, so over the years, petrol car engine and diesel car engine has a different objective, because for petrol car engine, okay, the combustion is literally controlled by the spark plug. But for diesel engine, the objective is actually to control and make it stable as possible for the ignition. Okay, and so the mini combustion will take place and push the piston out. This is called a working stroke. Okay, so this piston will be connected to your drivetrain, your gears, your wheels, which then drives the car. All right. So after all this happens, there will be exhaust inside, and then you'll move on to the last stroke, which is the exhaust stroke. Okay, so the piston push back in, the other valve will open up, and all the exhaust gas will come out, and then you'll be passed out from the exhaust pipe. All right, so this is called a 4-stroke internal combustion engine, typically for a car. Okay, but at this point in time, some of you might have a question. How is this a non-flow process? Because previously from the other slide, I've actually mentioned that the non-flow process is one whereby the fluid is not allowed to cross the boundary. But in this case, clearly the fluid is actually coming in and coming out. Okay, so something that I need you to take note over here is that for this thermodynamic analysis, okay, it actually only occurs for the working stroke. This working stroke is the stroke whereby the energy conversion process takes place. All right, so there is a thermodynamic process happening in here. And when this happens, the valves are closed. The air fuel mixture are not allowed to move in or out. Okay, So in this case, the chemical energy of the air-fuel mixture, okay, is released and transferred into the kinetic energy to move the car. Okay, of course, you can also analyze the second stroke, which is the compression stroke. Okay, because it's also a non-flow. All right. In this case, the piston does work on the air-fuel mixture. All right, but the main interest over here is actually the third stroke, which is the working stroke. Okay, so of course, other than the four-stroke engine, there's also two-stroke engine, one-stroke engine, or even three-stroke engine. Okay, the two-stroke engine is actually more common for motor vehicles, motorbikes. Sorry. So for the two-stroke engine, actually the concept is almost similar. It's just that it combines the first two together and the last two together. So it happens concurrently. All right, Ken. So since this is a four-stroke engine, so typically when you open the engine itself for a car, there should be four of these pistons inside. Why? Because as you can see, because it's four-stroke, but what happens? Only the third stroke produces power. So if imagine if we only have one piston, then we only have power for a quarter of the time, which is not favorable. Correct? So therefore, to solve this problem, we have four different cylinders operating not in synchronous, okay, with some time lag or time delay, so that to make sure that every single time we have power. All right, so this is an example of a non-flow process. Okay, so let's move on. Okay, so now we have seen an example of a non-flow process. So the next thing we are going to do is, again, we are going to develop the mathematical equation for this non-flow process. Okay, so for just now the non-flow process, you see that the fluid actually goes from state 1 to state 2. All right. So it goes from state 1 to state 2, and the internal energy of the fluid depends on the pressure and the temperature. So there is a certain change from 1 to 2. So we have to represent this change. Okay, so this change will be represented by the internal energy. U2 minus U1. Okay, so you see, if I open up, if I draw a schematic, initial is U1, final is U2. So the fluid actually undergoes some change from U1 to U2. Okay, so this change will be accompanied by work and heat exchange. All right. So this work and heat exchange is represented by the right-hand side. Okay, so again, for those who are not so fond with the summation sign, you can just simply write it as U2 minus U1 is equals to Q12 minus W12. All right. So some of you might ask, what is this 1, 2 over here? What is this 1, 2 over here? So this 1, 2, okay, actually represents the total heat transferred or the work transferred from state 1 to 2. So these two terms are actually what we call process dependent. These two terms on the left, which is U2 minus U1, is what we call state dependent. It depends on the state, initial and final. Okay, but Q12 and W12 is process dependent. All right. So this will be the equation we use for a non-flow process. Okay, let's move on. Okay, so we're going to look at one simple example for this non-flow process. So if we have a closed system that produces work amounting to 600 kilojoule, while the heat energy amount is 1000, is transferred to it. Determine the change of internal energy of the fluid and state whether it's an increase or decrease. So very simple, we'll apply the equation. Okay, so we are given that Q is 1000. Q in this case is Q in, so it's going to be positive. So when we plug in, it's going to be positive 1000. W is W out, so again, it's going to be positive. So when I plug in, it'll be positive 600. Take note, do not change the negative sign here. Leave it. This negative sign belongs to the equation. You shouldn't change it. Okay, so in this case, we'll get 400 kilojoule. All right, so therefore, since U2 is more than U1, the internal energy has increased. Okay, simple example. Let's move on. Okay, so we have already studied the thermodynamic cycle, and then we have also studied the non-flow process. The last process that we are going to talk about is actually a open flow process, or analogous to it is called the open system. Okay, so we have open system. So this open system, okay, as you might have already known it, both heat and work can transfer across the boundary, and on top of that, the fluid can also cross the boundary. Okay, so any process that undergoes by an open system is called a flow process. Okay, so for this flow process, there's actually two types. One is called the steady flow process. The other one is called the unsteady flow. For the purpose of this module, we'll be only looking at the steady flow process. All right, because unsteady flow process involves transient states. Okay, and we need to bring in differential equation. That one, we'll leave it to university. So now we are just going to solve for simple equations using the steady flow process. So for this steady flow process, what are the conditions? Okay, the conditions we have here is that the mass of the fluid flowing past any section, okay, must be constant. Okay, so basically, to sum up the first statement here, what we are talking is that the mass flow rate must be constant. Next, the properties of the fluid at any particular section must remain constant. Okay, so if let's say we have a system here, okay, represented by this box. What this means is that within this box, okay, at different positions, there can be different state values. Let's call this 1, 2, and 3. So yes, even though within this system, all the values are different, but at steady flow process or at steady state, the 1 must always remain the same. So if let's say the pressure is at 1, the pressure at 1 is always 10 bar, it must remain 10 bar throughout. If the pressure at 2 is 2 bar, it must remain 2 bar throughout. Same thing, if the pressure at 3 is 1 bar, it must remain 1 bar throughout. Okay, so this is what this second statement is trying to say. So don't be confused. It's not saying that the whole system must only have one value or one unified value. Okay, but it's saying that the system is at steady state so long as every different section maintains its own value throughout. Okay, Ken? Of course, the last statement here is that all work and heat must occur at a uniform rate too. Okay, so these are the three basic principles that we must follow for a steady flow process. So let's move on. So next, again, we want to develop the equation for a steady flow process. Okay, let's look at one example over here, which is a steam boiler. Okay, the concept of steam boiler is very simple. Basically, it's just a water tank. Okay, and then we'll heat it up using a furnace. Okay, so heat is applied. All right, so this is a steady flow process because there is water going in and steam coming out. All right, so to develop the equations, the first thing that we must take note is that the mass flow rate must remain constant throughout. So as I mentioned just now, all right, the mass flow rate must remain constant. Okay, so the next thing, let's go to the next slide. Okay, so again, the same concept over here. The first equation that we apply is actually the continuity of mass equation. So as I mentioned, since the mass flow rate must be the same, okay, so for any steady flow process that we are looking in this module, okay, the mass flow rate going into the system must be equals to the mass flow rate going out of the system. All right. So in this case, if you're interested, actually we can calculate the mass flow rate by using this equation, which is m dot equals to C times A over V. Okay, so how do we derive this equation? Okay, I'm just going to do a quick simple derivation here. Okay, so we can actually start off from mass is equals to big V over small v. All right, so if we want to take the rate, basically we are talking about m dot must be equal to V dot over V, small v. So the mass flow rate is the volumetric flow rate divided by the specific volume. So for the volumetric flow rate, okay, it can be replaced by the equation cross-sectional area times C over V. Okay, so the volumetric flow rate is actually given by AC. Okay, so how do we actually visualize it? Okay, so if let's say we have a pipe with water flowing through, the cross-sectional area is A. Okay, so if the water is flowing at a velocity of c meter per second, so every 1 second, this cross-sectional area is being swept across by c meters. So this volume, which is c times A per second, will actually give you the volumetric flow rate. And you divide it by specific volume, it will give you the mass flow rate. Okay, so this is just a side topic. We'll come to this later on. Most importantly, for all steady flow equation, all right, we are going to apply this. M dot in must be equals to M dot out. Okay, let's move on. So next, let's look at the energy transfers that will occur within the system. All right. So if we talk about the energy transfer, okay, we can actually very quickly identify 4 of them, which is heat out, work out, heat in, and work in. So typically speaking, the steady flow process, okay, generally will be the same as a non-flow process in terms of these 4. So heat can go in or come out, work can go in or come out. Okay, but the only thing that is different is that the fluid itself can also enter the system, and the fluid itself can also exit the system. So when the fluid enters the system, it actually brings along with it 4 different types of energy. We have the pressure energy, the velocity energy, we're just going to call it velocity now, the internal energy, and also the so-called height energy. Same thing, when the fluid comes out, you'll bring out along with it the pressure energy, the velocity energy, the internal energy, and also the height energy. Okay, so the difference here between a steady flow process and a closed system or a non-flow process is that the fluid actually comes in and out. And when the fluid comes in and out, you'll bring along 4 different types of energy. Okay, so let's take a closer look at what these 4 different types of energy is. Okay, so as I mentioned, there's 4 different types of energy that you'll bring in. First one is actually the internal energy. So the internal energy is associated with the energy of the fluid itself. All right. So if you want to talk about the rate of internal energy, it's simply m dot times U1. That is the rate at which it's bringing the internal energy into the system. The height energy, which is associated with the height term, is actually something that we know. It's actually called the potential energy, which is given by mg times height. In this case, we will not use h, but instead we will use the word z, because h is reserved for something else. So m dot gz will be the potential energy. And next, the velocity energy, okay, again, is something that we know is called the kinetic energy. The formula is supposed to be half mv squared, but in this case, we will use it as half mc squared, by c is the velocity. All right. And the last thing that we mentioned just now is actually the pressure energy. So how do we visualize this pressure energy? Okay, it's actually the amount of energy used to push the fluid into the system. It's just like you, if you want to enter a door, okay, you must actually push the door in. So the water requires energy to push itself into the system. Okay, so if you take a closer look over here, okay, to visualize this, all right, okay, the pressure is exerted here, used to push a delta volume into the system. So therefore, the equation is given by PV. All right, and to represent the rate of energy, you'll be given by m dot PV. Okay, so this is the total energy going into the system, brought in by the fluid. And on top of that, okay, we also have our generic heat and our generic work. Okay, don't be confused between this work and this work. They are not the same. This work is generic work. It can be worked by a turbine, it can be worked by a compressor, it can be worked by a certain rotary blade that is placed within the system. But this work is the work required to push the fluid into the system. Okay, so this will be the total energy in to the system. Okay, so if we want to apply the energy balance, okay, because this is the first law of energy, first law of thermodynamics. So again, we are talking about rate of energy in must be equal to rate of energy out, because energy cannot be destroyed or created. It must be conserved. So whatever goes in must be equal to whatever comes out. All right. So then what comes out? So if we were to do it for the out, okay, before that, let me write the complete equation for the in. So for the in, okay, it will be Q in, W in, the rate of energy, internal energy, the potential energy, sorry, not potential, okay, again. Uh, okay, let me just write it. Okay, so Q in, W in, the first term here is the internal energy. The second term here is your work done to push the fluid in. The third term here is your potential energy. Your last term here is your kinetic energy. So the energy into the system will include Q in, W in, MU1, mp1v1 mgz1 plus mc1 squared over 2. So of course, we'll expect the same thing to happen for the out. Okay, so for the out, what we will have here is our Q out, generic Q out, W out, and we will also have the internal energy brought out by the fluid leaving the system, the work done to push the fluid out of the system, the PE, the potential energy brought out by the system, by the fluid, and the KE. All right, so then with that, we can equate E dot in equals to E dot out. Okay, but there's a simplification that we can make over here. Okay, if you remember, H is equals to U plus PV. Okay, so what is H? H, we've actually discussed it in the previous chapter. We call it the enthalpy. So the enthalpy is actually the sum of internal energy plus the work done to push the fluid into the system. So usually for a system that flows, open flow system, we seldom quantify the fluid energy with internal energy. We need to quantify it with something called the enthalpy. All right, Ken. So enthalpy is a form of energy, okay, that is usually associated with fluid that is moving. All right, Ken. But instead, if we are talking about a static system, a closed system, usually we only quantify it with U, which is the internal energy. But if we are talking about a system that is flowing, then we will use the word enthalpy. All right, so what that means to say, we can replace this U1 plus P1V1 and U2 plus P2V2 with H1 and H2. Okay, so we equate the left-hand side to the right-hand side, we will get this super long equation. Okay, so Q in plus W in equals to, all these are dots, okay, because all these are rates. M dot times H1 GZ1 C1 squared over 2 Q dot out W dot out M dot 2 H2 GZ2 C2 squared over 2. So this, ladies and gentlemen, is the steady flow equation. Don't be afraid, don't be scared, because this equation is provided in the exam. Okay, you just need to understand what each of these terms are. Okay, so if we have understood the equation, okay, the next thing we are going to do is to apply it to a question. Okay, so if you have an open system, the fluid flows through the system at 17 kg per second. Okay, and the power developed by the system is 14,000 kilowatt. The specific enthalpy of the fluid at the inlet and the outlet are 1,002 and 360 respectively. And the velocity of the fluid at the inlet and outlet are 60 and 150 respectively. Okay, so before we actually go into answering the question, which is this part, let me try to write down the terms first. So today, we are given that m dot 1 is equals to m dot 2, which is equal to 17. So because the mass flow rate has to be the same for a steady flow system. So m dot 1 and m dot 2 must be 17. Okay, we are also given that W dot, in this case, is power developed. So it will be W dot out is equals to 14,000 times 10 to the power 3 watts. All right, or maybe I don't use the word watts. I can change it to SI units or derived units to be joules per second. All right, next, we're also given that the specific enthalpy at the inlet, H1, is 1200 times 10 to the power 3 joules per kg. And we are given H2 is 360 times 10 to the power 3 joules per kg. So try to write all this down first by yourself in SI unit. We are also given that C1 is 60 meters per second. And C2 is 150 meters per second. Okay, so you must be able to associate the symbols with the terms. Okay, then we will go into the question. Find the rate at which the heat is rejected from the system. Okay, so how are we going to do it? Very simple. So since we have all these values, all right, we are just going to apply the two equations that we have learned. Okay, the first equation is actually just merely write out. We have already written it, but we're just going to write it again. Is the conservation of mass equation. What goes in must come out. So m dot 1 must be equals to m dot 2 equals to 17. Next, we'll apply the steady flow equation. So remember, for this open flow system, there's only two equations, 1 and 2. So we're going to write down this equation. Okay, so before we plug in the values that we have written just now, okay, we are going to do some simplification. Simplification is done when the values are not given to us, or the values are specifically said that is 0. Okay, so if you look back at the question, Q dot in is not given, so it must be 0. W dot in is not given, so it can be assumed to be 0. All right. It is also said that from the question, the potential energy change is negligible. That means the height is the same. All right. So with that, with all this, we can actually do some cancellation. So I'm going to do some cancellation from here. Q dot in, gone. W dot in, gone. GZ1, gone. Q dot out, remain. W dot out, remain. H2 remain. GZ2, cancel. Therefore, after we do the simplification, we land ourselves here. Then we are ready to plug in the values. So we simply plug in the values accordingly, and we can solve for our Q dot out. Okay, so for this solution here, the solution made Q dot the subject. Okay, and move the rest of the terms to the right hand side. Then the remaining part of the question is just simply plugging in the values. So that's why I say the value identification is very important. Okay, so we just plug in the values that we've identified. M dot 1 was 17. H1 was 1002 times 10 to the power 3. C1 was 60. M dot 2 was 17. H2 was 360 times 10 to the power 3. All in SI unit, remember. C2 is 150. And W dot out was 14,000 times 10 to the power 3. So this becomes a simple problem of just plugging in the values. And then we get the final answer. All right. The second part of the question requires us to find out the cross-section area of the inlet pipe. So remember, just now we have actually seen this equation. M dot, I derived it very quickly for you, was AC over V. So we can make use of this equation to find out the cross-section area. This equation here is given in the formula list. All right. But what we need is the cross-sectional area. So area, all right, is if you do some manipulation, will be M dot V over C. Okay, so you have to derive this in exam yourself if you want to use it. So today, if you want to find the inlet, so all will be 1. I must use all the 1 values. Okay, so M dot 1 is 17. V dot 1 is given to be 0.5. And C1 is given to be 60. So with that, I can determine the cross-sectional area of the inlet pipe. All right, so simple question. You just have to do practice, then you can do it. Okay, the next example that we're going to look at over here is example 2.4. Fluid flows steadily at a rate of 0.4 kg per second through an open system. All right, so let me just highlight. All right, entering at 6 meters per second with a pressure of 1 bar and a specific volume of 0.85 and living at 4.5 meter per second with a pressure of 6.9 bar and a specific volume of 0.16 meter cube per kg. The specific internal energy of the fluid leaving is 88 kilojoule greater than that of the entering. 59 kilojoules per second of heat is rejected and potential negligible. So again, let me write down the values that are given to us first. All right. So the first thing that we can write is m.1 is equals to m.2 must be equals to 0.4. These are your mass flow rates. Okay. Next values that we are given is 6 meter per second. So C1 is 6. Okay, we can go sequentially. Okay, P1 is 1 bar. So again, please change it to SI unit times 10 to the power 5 Pascal. V1 is 0.85. Okay. And leaving, all right, C2 is 4.5 meter per second. P2 is 6.9 times 10 to the power 5 Pascal. And V2 is 0.16 meter cube per kg. All right. So these are the values given to us. And on top of that, we are also given that the specific internal energy leaving is 88 kilojoules per kg greater than that entering. So today we are not given the enthalpy. Previous question we are given H1 and H2. Now we are given in terms of internal energy, and what's more is that they are given in terms of the difference. So how do we write down this difference? So since the leaving is greater than that of the leaving, the leaving is greater than that of the entering. That means U2 must be bigger than U1. So this difference here, we can write it as U2 minus U1 is equals to 88 times 10 to the power 3 joules per kg. So this is how we write the difference. Be careful, okay, it can be tricky sometimes. So leaving is greater than that of the entering. So U2, which is leaving, must be bigger than U1. So U2 minus U1 is 88. All right, so once we have identified all these values, we can proceed to apply the two equations for the question. So which two equation? First one is your conservation of mass. Okay, for formality, we'll just write down m.1 is equals to m.2. All right. Applying steady state energy equation is the second equation. So this is 1 and this is 2. So we'll do some simplification. So Q dot in is not given, so it's 0. W dot in is not given, so it's 0. Potential negligible. All right. So with that, we can do some cancellation. Q dot in don't have. W dot out don't have. GZ1 don't have. GZ2 don't have. Okay, so the other terms are what is remaining. All right. So take note, this is in terms of enthalpy. All right. So moving on. Okay, so if we want to calculate the work in, okay, again, the solution here did a simplification. It made W in the subject and moved the rest to the right-hand side. Okay, so the next thing that the solution did was to group up the H2 and H1. Okay, let me just clear this and write H2 and H1. Okay, basically they split. So in this case, if you open this up, is m.2 H2 plus m.2 C2 square over 2 minus m.1 H1 minus m.1 C1 square over 2. So the solution here group m.H2 and m.H1 together to give you m.H2 minus H1. And the solution group m.2 C2 over 2 and m.1 C1 over 2 together. It gives you this. Okay, so we actually have everything over here other than H2 minus H1. So we need to go and compute my H2 minus H1. So how can we do it? So H2 minus H1, okay, if we break it up into U plus PV, you'll be in this form. U2 plus P2V2 minus U1 plus P1V1. So again, we group up the U2 minus U1. So we group this U2 and U1 together to give you U2 minus U1. And we group P2V2 and P1V1 together to give you P2V2 minus P1V1. All right. So from there, we can actually plug in the values because we are given the difference of U2 minus U1 as shown in the first slide. So U2 minus U1 is 88 times 10 to the power 3. P2 V2 is just simply plug in the values. P2 V2 P1 V1. So we can actually get the delta difference of H2 minus H1. So once we get difference, we can just plug in the values. So Q out we have, which is 59 times 10 to the power 3. M dot 0.4, H2 minus H1 calculated M dot 0.4, C1 4.5, sorry, C2 4.5, C1 is 6. Plug in everything and we get our answer. Remember, everything must be in SI unit. So today, if they give you in terms of internal energy, pressure, and specific volume, you need to calculate this part, U plus PV. All right. Okay, and then the last part here, again, is to calculate the cross-sectional area, which we are going to apply the same equation, okay, which is this two. So for the inlet and outlet, inlet I must use A1, V1, C1, and outlet I must use A2, C2, V2. Okay, so this most of the time, the second part here is 3 marks for you. All right, Ken? So if not, that's all for this lecture 2. Please proceed to do your tutorial. Okay, hopefully you have a better understanding of what the first law of thermodynamics is. In a nutshell, basically, it's just the conservation of energy. But what we are trying to do here is we are trying to formulate equations for this conservation of energy. So what we formulate here today was for a thermodynamic cycle, non-flow process, and a steady flow process. Okay, thank you very much. Hope you enjoyed the lecture. Bye-bye.